So, we are looking at the orthogonal relation between the Bessel functions. We have seen we have shown that they are actually orthogonal to each other when they are different. So, we look at the other part that when you take the same function in that the relation that's when you take lambda I equal to lambda j, that is same as I equal to j. The case when I equal to j, what if I equal to j? In this case what you have is 0 to L x times j alpha of lambda I x dx. So, alpha I is both are same, this is actually equal to. So, we will see that this will be equal to some number, that is, let me write this a square by 2 sorry L square by 2 j square n plus 1 of lambda I L, or this is same as L square by 2 j n minus 1 square of lambda I L. So, not n, this is alpha. So, this is alpha, this is what you will get. Okay. So, this is the either this or this. So, we will show how it is done, okay, this part. So, this part what we do is you take the equation. So, we only have one function. So, that is j alpha of lambda I x satisfies the Bessel equation, that is x square, that is j alpha double dash of lambda I x plus x j alpha dash of lambda I x. Okay. So, let us call this maybe some function of x u x. Okay. So, then you have u double dash, then it will be easier for you. So, u x u dash plus x square. So, you have here this is lambda I square x square minus alpha square into u of x equal to 0. So, u is j alpha of lambda I x. Okay. What I do is for this equation I multiply simply 2 u dash something. Okay. So, if this is 0, so both sides I multiply 2 u dash, multiply 2 u dash, that is 2 times j alpha dash of lambda I x. So, if I do both sides to get what you get, if you do this, you have 2 u dash x square 2 x square, rather if you do it 2 x square u dash u double dash plus 2 x u dash square plus lambda I square x square minus alpha square times 2 u dash equal to 0. Okay. So, the next step is you can see that 2 u dash, right. So, you have this one. So, you just have to write this in a simplified manner, that is, so you can see that x square u dash square, what is the derivative of this? Derivative of this, if you consider, this is equal to x square that is 2 x. If you do this, this is 2 x u dash square plus x square. So, you have 2 u dash u double dash. So, you can see that this together. So, these two parts you can write like as a derivative. Okay. So, what happens, the other part is d dx of lambda I square x square u square. What is this one? This one lambda I square x square 2 u dash, if I differentiate u square. Now, one more term is there, that is lambda I square, you differentiate x square. So, you get 2 x u square. So, this is what you need. Okay. And then so I can replace this part with this. So, this implies, so you can rewrite dx of lambda I square x square u square minus 2 lambda I square x u square. I can replace with 2 lambda I square x square u dash. Okay. So, what is left is minus 2 alpha square u dash. This I can write like minus d dx of alpha square u square. Okay. So, replace each of this with alpha square, this is with this as a derivatives. If I do this, you can rewrite the first two terms. I can write like d dx of x square u dash square, okay, plus d dx of lambda I square x square u square minus 2 lambda I square x u square. That is what is my this term, first term in the bracket, and what is left is finally minus d dx of alpha square u square equal to 0. So, derivatives you put it together. So, what you have is this, you take it the other side. So, you have lambda I square x u square equal to d dx of x square u dash square plus lambda I square x square u square minus alpha square u square. Now, you differentiate both sides from 0 to L dx, 0 to L dx. This is equal to x square u dash square plus lambda I square x square u square minus alpha square u square. You put the values from 0 to L. Now, you see that u at L is 0. Okay. So, this is nothing but they will give you L square u dash at L square, okay, minus. So, when you put 0, this is 0 and this is 0, and you have minus minus plus alpha square u at 0 square. They do this properly. So, you have lambda I square 2x square. So, 2x square lambda I square u dash, I replace with this minus 2 lambda I square x u square. Okay. So, you have x square this alpha square u square, that is finally alpha square u square. Okay. So, this is what you get. So, when you replace x by L, u is 0 at L, u is 0 at L. So, this will contribute to L square this. When you put minus of this, when you put x equal to 0, this is 0, this is 0, this is going to be plus alpha square this one. So, this is what you have. So, this divided by 2. So, this implies, so what you get is 0 to L lambda I square comes out. So, this is a constant. So, you have x, u is j alpha of lambda I x square, okay, dx is equal to 1 by, so that is L square by 2 lambda I square. This is j alpha dash of lambda I x whole square plus alpha square by 2 lambda I square into j alpha of lambda I at 0, okay, this square. But j alpha at 0, u at 0 is also 0. Okay. So, j alpha at 0 is 0, since j alpha of x, if you actually see it as a sum which has x power 2m plus alpha, alpha is positive. Okay. So, you can see that this is 0, j alpha, if you put x equal to 0, this is 0. Okay. So, this will be actually 0. So, this is what you get. So, this is equal to L square by 2 lambda I square j alpha dash of lambda I x whole square, lambda I L, right. So, this is lambda I L. This is a fixed thing. So, lambda I L whole square. Okay. This is what you get. So, now how do you find this and make it equal to this type alpha plus 1 alpha minus 1. This is where we use those properties of those properties of these properties. If you use properties of the Bessel functions, you can actually get those things. You simply differentiate 1. So, if you differentiate this, what you are getting end up is x power alpha. So, you just expand this derivative, okay, which is equal to this. Either of these you can use, one of these you can use, and to show that to get this one. Okay. So, I will just do one I will just use 1 to find this value j alpha dash. So, let us take this first, what is that, so recurrence relation is d dx of x power alpha j alpha of x equal to x power alpha j alpha minus 1 of x. So, let us choose this one. Okay. If you expand this x power alpha j alpha dash of x plus alpha into x power alpha minus 1 j alpha of x, that is the derivative, the left hand part I have written. You have x power alpha j alpha minus 1 of x. Now, you cancel both sides x power alpha. So, to get j alpha dash of x plus alpha by x j alpha of x plus j alpha minus 1 of x. So, this is what you get. Okay. So, now you use that this one, if you use j alpha dash at put x equal to lambda I L, which is equal to minus alpha by lambda I L j alpha of lambda I L, and I know that this is 0 plus j alpha minus 1 of lambda I L. Okay. So, you want this square and this whole thing is 0. So, this square. Okay. So, this is exactly what you have. So, you need this is equal to lambda square by 2 lambda I square j alpha minus 1 of lambda I L whole square. So, maybe I missed this part. So, what you have is, that is what you have, 2 lambda I square, that is also there, lambda square by 2 lambda I square. So, you have actually lambda I square is also here, lambda I square, that is the result. Okay. I did not make any mistake here. So, the mistake comes here. So, actually you have when you differentiate this, you have 2 lambda I square x square u double dash d dx of u dash 2x square u dash. That's fine. Huh? Yeah. So, when you are doing this u dash, so u dash, u is actually, u dash means d dx of u dash, u is u dash of x is, u dash at L is d dx of j alpha of lambda I x. This is j alpha dash of lambda I x into lambda I. Okay. So, when you are squaring it, so you have this is this whole square equal to this square into lambda I square. So, you have lambda I square comes here. Okay. So, that goes. So, this is what you have. So, otherwise it is fine. So, you do not have this lambda I square. So, that is how you get this lambda without this lambda I square. Similarly, if you use other recurrence relation, if you use the other property, So, if I use this one, if I use this property, you get this result. Okay. If I use the other result, that is d dx of x power minus alpha j alpha of x, which is given as x power minus alpha times j alpha plus 1 of x. If I use this one, I get other result, which is L square by L square by 2 j alpha plus 1 at lambda I L whole square. Okay, both the things. So, if you use this one, I get this one. Because I use this one, I got this result. Okay, that is what is this integral value. This is this integral value. Okay, so that's what we find. So, this is what we derived. So, if I use the other property, you can get this result that you can do yourself. So these are the some important properties of Bessel functions. We have seen some special case when 2 alpha equal to the difference between the initial roots. 2 alpha is 1, 3, 5. Okay. So, the general solutions, the solutions are 2 linearly independent solutions are j alpha x, j minus alpha x. Okay. In this special case, for all these cases, you need, if you know 1 j minus half, when alpha equal to half, okay, when alpha equal to half, you get j half x and j minus half x. So, if I know this, I can get from the recurrence from those two properties, I can get all other values 3, 5. So, I can get, if I know this, if we know for alpha equal to this one, we can find all other things. Okay, we can find all other things like j n plus half and j minus n minus n plus half. Okay, n is from 1, 2, 3 and so on of x by recurrence relation. So, that is called recurrence relations. Just by properties 1 and 2, if you use, you can get them and then you can use. So, how do we get this? We can nicely find the formulas for j half and j minus half. That we do by simply consider the equation, Bessel equation in this case. Bessel equation is x square y double dash plus x y dash plus x square minus alpha square is 1 by 4 y equal to 0. So, this is the equation. So, if I choose some z equal to root x into y, let this be the transformation. Okay. So, let a dependent variable I am changing to z of x. Okay. If I use that z of x, so if I use this transformation, then what you have is dy by dx equal to dy by dx is dy by dx dy by dy by dx, this is dz by dx. I want dz by dx. Okay. So, dz by dx, you can write dz by dx. So, how do I transform this? So, you simply replace d dx of z is root x y. So, this you have root x dy by dx plus 1 by 2 root x into y. That is what you replace, dz by dx. Okay. And then what you need is a d square z by dx square. This is equal to d dx of dz by dx is we already found. So, that is dy by dx plus 1 by 2 root x y. This is equal to 1 by 2 root x dy by dx plus root x d square y by dx square plus dy by dx 2 root x dy by dx, okay, plus 1 by 2 into x power minus half. That is, what is the derivative of x power minus half? That is minus half x power minus 3 by 2. So, that is going to be minus. So, 1 by 2 into 1 by 2 square, that is going to be 4 x power 3 by 2. This into y. This is what you have. So, substitute for dy by dx. From this you can calculate dy by dx. So, this is 1 by root x dy by dx plus root x d square y by dx square minus 1 by 4 x cube x 3 by 2 y. Or rather, so instead of these calculations, we can consider you can consider if you choose this transformation, I can get dy as z by root x, so that you can calculate dy by dx as directly. So, you have z minus half x power minus 3 by 2 z plus 1 by root x dz by dx. Similarly, you can replace, you can get this d square y by dx square as 3 by 4 x power minus 5 by 2 z plus minus 1 by 2 x power minus 3 by 2 dz by dx plus rather minus half x power minus 3 by 2 dz by dx plus 1 by root x d square z by dx square. So, once you calculate this dy by dx and d square y by dx square, you substitute into the equation. So, if you substitute into the equation, so you get x square y double dash, that is x square into this part. So, you get 3 by 4 x square will give you 1 by root x z by root x, okay, minus this together will give me minus 1, that is 1 minus 1 x power minus 3 by 2 plus 2. So, that is root x times dz by dx plus x power 3 by 2 times d square z by dx square. So, this is what is x square y double dash plus x times dy by dx, you can write this part. So, for this you multiply x. So, we have minus 1 by 2 root x z plus root x dz by dx, and then plus what you have is x square minus 4, x square minus 1 by 4, y is z by root x equal to 0. So, you see that nicely this transforms into simpler equation. As you see, multiply, so you can see that x root x dz by dx cancels, and this part minus 1 by 4 z by root x, okay, and 3 by 4 z by root x, and minus 1 by 2 z by root x, this becomes 0. So, 3 by 4 it becomes minus half minus 1 by 4 z by root x, this part will be 0. So, what you are left with is simply x 3 by 2 d square z by dx square plus x 3 by 2, because x square divided by root x into z equal to 0. So, this will give me now x 3 by both sides you can cancel, you get z double dash plus z equal to 0. So, if you use this transformation, the equation given Bessel equation when alpha equal to half becomes simpler one. So, this we know zx as a general solution of this equation is c1 cos x plus c2 sin x. So, once I know z, what is my yx, simply c1 cos x by root x plus C2 sin x by root x, because zx by root x, z by root x is my general solution y for the Bessel equation. So, this is the general solution. Fine. So, this is the general solution of the what you found so far is the general solution of the Bessel equation, but we already know that j half and j minus half are the two linearly independent solutions. Okay. J half and j minus half are two linearly independent solutions. Here now I found that cos x by x, sin x by x, root x are two linearly independent solutions, because these two are linearly independent. So, this is the general solution. So, this is how you get. So, I found these two are linearly independent. So, that means this must be one of them with some constant multiple. Okay. So, this I should be able to write this in terms of this and this in terms of this. Okay. So, let us do one in terms of the other. Okay. What we do is, so we know that x half so that is what is right. So, you know that y is, so you know that y is z by root x, right. So, y, so we see that, let us see, y of x is, the transformation is z of x by root x. Okay, this is the transformation. That means my yx, if I know that yx, y is satisfying the Bessel equation. So, that is j half of x is one solution. Okay. So, this is the solution for y, which is equal to z. Some z will be so if I choose my yx, so let me explain properly. So, you have this implies zx equal to root yx into root x. Okay. So, if I choose y as j half of x into root x is also a solution. Okay. That means zx will be like this. If I choose in the for y, if I choose as I know that j half is the solution. So, once I choose this, root x into j half is the solution of this transformed equation. Okay. This satisfies z double dash plus z equal to 0. So, that means this is the solution of this equation, one solution. So, that implies j half of x into root x is equal to some linear combination of some d1 times cos x by root x, because these are the solutions, not root x. What are the solutions of z double dash plus zx? Cos x plus d2 sin x. Put x equal to 0, that will give me d1 equal to 0. Okay. So, that means this is not true. So, this implies root x j half of x is actually equal to d2 sin x. So, how do I find my d2? So that I can get my j half in nice expression. So, this implies you write simply d2 as root x j half of x divided by sin x. Okay. If the d2 is constant, now if I can take this limit x, this should be true, this should be a constant, even at x equal to 0 or any other value, it should give the same value. Okay. So, at x equal to 0, if I take, this is well defined at x equal to 0, well defined at x equal to 0. So, I can consider this limit, this is equal to limit x goes to 0, this I write sin x by x. So, that if I write sin x by x, I should have j half of x by root x. Okay. These two are same. So, this is nothing but, now you see that bottom, this limit goes to 1. Okay. This goes to 1 and this goes to simply 1. What is the value? So, this you have to calculate. Okay. So, this is actually equal to limit j half of x by root x as x goes to 0. Okay. So, we will find what that j half of that. Okay. So, 1 by root x j half of x is actually equal to, what do you get? You will get sigma m is from 0 to infinity minus 1 power m x by 2 power 2 m plus alpha, that is half, okay, divided by m factorial into gamma of m plus 3 by 2, m plus half plus 1. This is what is the j half of x. I am dividing with 1 by root x. This is my j half. If I divide with this thing, this you will get simply m is from 0 to infinity minus 1 power m x by 2 x power 2m plus x power 2m divided by x goes, okay, root x, and I have 2 power under root, okay, 2 power 2m plus half into m factorial gamma m plus 3 by 2. So, this is what for which I am looking for the limit. Okay. So, this is, if you take the limit x goes to 0, this limit x goes to 0. So, what happens? So, if I see, these are the terms starting from constant plus x square x power 4. All the x square x power 4 coefficient, everything will be 0 as x goes to 0. Only that constant term, that is corresponds to m equal to 0, you have simply 1 divided by root 2 m factorial, 0 factorial is 1, gamma of 3 by 2. This is 1 by root 2, 1 by 2 into gamma half. Okay. So, this is nothing but, so 2. So, if this becomes 1 by root 2, that becomes root 2 goes to numerator into gamma half. So, gamma half is root 2 by pi. So, gamma half is root pi. Okay. So, this you get root 2 by pi. So, once you get this root 2 by, go and put it. So, this is what you get as root 2 by pi. So, that implies, so from here you can get j half of x. J half of x is nothing but root 2 by pi sin x by x. Okay. So, if you want gamma of gamma half, how do you find gamma half? Gamma z plus 1 is integral 0 to infinity, that is what we defined yesterday, right. So, you have gamma is e power minus x, x power z minus 1, z, x power z dx. So, if you want gamma half, you take gamma z is z minus 1 dx. So, you take z equal to half. So, gamma half, if you calculate, so 0 to infinity e power minus x, x power z is half. So, you have minus half dx. So, you just do the integration by parts and you can find that its value is 1 by root pi, you will get. Okay. So, you can do that as an exercise. So, this is gamma half is root pi. So, you will get that. So, you will use that to get this one. Now, to find what is j, what is the next question is j half of x. What is my j half of x? This also you can show that root 2 by pi cos x by x. Okay. How do I show that? That is not difficult to show. So, we use the property that what is the property that root x, right, this should be root x, sin x by root x. So, this here also cos x by root x. Okay. This is what you get. So, this is what you want to show. Okay. To show, we can also show that this one, this is, how do we show this one? So, we use this property d dx of x power half x power alpha into j alpha okay. This is equal to x power alpha, and this is j of alpha minus 1, that is going to be minus half of x. Okay. So, you want this one. So, the left hand side you replace. What is the left hand side? This is the derivative of, you can see that j half, this we know already, this is what we proved. Okay. Root x into j half is root 2 by pi sin x, which is j half j minus half of x from the property 1. Okay. This is from the property 1. So, this gives me, what happens this, so right this, so property 1 if you use, this is what you will get, but I know that dx root x into j half is, I already know from here. So, if you do that, this is nothing but root 2 by pi cos x equal to root x j minus half of x. So, implies j minus half of x is root 2 by pi x cos x. This is what you will get. Okay. So, here, so you have already known this one. Okay. This is what you have shown. So, you have nicely get j half and j minus half. Okay. So, we will have use the property 1 and property 2. You just get just expand the property 1 and property 2 and add and subtract them to get 2 more relations. Using that, you can actually get all j 3 by 2, j 5 by 2, all j 3 by 2, 5 by 2, or j minus 3 by 2, j minus 5 by 2, and so on. Okay. All these things you can get it as nice expressions in terms of cos x and sin x and root x. Okay. In terms of this, you can express. We will see this in the next video.